So we're jumping into chapter 4 in our textbook, and we're not doing every section in this chapter, and we're just going to do a couple of sections, and this should be review. And we've talked about linear functions or linear equations before. Now we're just putting it as linear functions. So if you're looking at a linear function, instead of writing it as y equals mx plus b, remember we can put things in function notation, and we can rewrite this as f of x equals mx plus b. So recall, this is the graph of a linear function is a line with a slope m, and our y-intercept is b. And its domain, there's no trouble spots. Our domain of a linear function is all real numbers. In the last chapter, we looked at finding the average rate of change between 2 points or on an interval. And this theorem, the average rate of change of a linear function. The linear function have a constant average rate of change. It's always changing at the same rate. That is the average rate of change of a linear function, f of x equals mx plus b. Our slope we can get by the change of our y value all over the change of our x value. And we denoted that with that triangle y all over triangle x equals m. We talked about lines increasing, decreasing, and constants, and what we know about their slopes in each case. So in here, increasing, decreasing, and constant functions. A linear function, f of x equals mx plus b, is increasing over a domain if the slope is positive. So we said if our slope is greater than 0, it increases. We stated that it decreases over our domain if the slope m is negative. So if our slope is negative, less than 0, the line decreases left to right. And if the constant, it's constant over the domain if the slope m is 0. So we have a horizontal line if it's equal to 0. So we can model using linear equations sometimes. So modeling with linear equations, if the average rate of change of a function is constant m, so it's always the same value that it's changing, a linear function f can be used to model a relation between the two variables as follows. So f of x equals mx plus b, where b is the value of f at 0, that is b equals f of 0, which when x is 0, that would be represented as f of 0. And that's where it's touching or crossing the y-axis. Okay, so let's pull up some examples. Okay, so in the following example, it states determine whether each function is linear or nonlinear. If linear, determine the slope. And so in this case, we're given our x and our y values of some function, and we want to know if it's linear or not. So notice our x values. Our x values are changing at the same rate, right? So -2 to -1, we're adding 1 here. -1 to 0, right? I added 1 there. 0 to 1, I'm adding 1. So the change in my x value, I notice I'm changing by 1. So my rate of change for x is equal to 1. So let's see if our y values are also constant. And so let's see what's happening to get from one y value to the next. So -4 to -3.5, I notice that I'm adding 0.5, right? From -3.5 to get to -3, I'm also adding 0.5. Here, -3 to -2.5, I'm adding 0.5. So each time I'm having the same rate of change. So the change in my y value is equal to 0.5 or a half. Because we have the same rate of change from each point, we can say that this is linear. And so our change of y over our change of x is equal to 0.5 over 1. Which is 0.5 or 1/2. Okay, so my slope here is 0.5. It's told me if this was a line that it wanted me to find the equation of the line. So we have a slope. Looking at this, I have my point, so I can actually see from looking at this point what my y-intercept is. When x is 0, my y value is -3. So my b value is -3. And so my equation of my line is f of x equals m, so 0.5 times x plus b. So in this case, -3. Let's pull another example. Okay, so in this example, we're given what f of x is and we're given what g of x is. And so in here, we're given that f of x is equal to the linear function f of x minus 1, and g of x is equal to the linear function -2x plus 5. Let's say it wanted us to find when f of x is equal to g of x. Well, to do that, we know what our f of x function is, right? This is our 4x minus 1. We want to know when is this equal to our g of x function, and our g of x function is -2x plus 5. So let's rewrite g of x -2x plus 5. So looking at this, we're trying to find out what x value, if we're to graph these, is this graph crossing each other. And so we have a linear equation. Solving linear equations, we get variables to one side, constants on the other. So looking at this, if I add 2x to both sides, I get 4x plus 2x is 6x. I want to add 1 to both sides, get the constant on the other side. So 5 plus 1 is 6. I get 6x equals 6, or x is equal to 1. So this is the x value where it crosses. And so I either want to look at what is f of 1, which should be the same thing, or I can look at what g of 1 is. So if we go in and we plug in 1 wherever we see an x in these functions, let's look at f of 1. F of 1, that would give us 4 times, I see an x there, we're going to replace it with 1 minus 1. So 4 times 1 is 4, 4 minus 1 is 3. So this would give us back 3. Or I just want to show it, g of 1. If we go into our g of x function and we plug in 1 wherever we see an x, we get this -2 all times 1 plus 5. Well, -2 times 1, right, is -2, and -2 plus 5 is 3. So f of x equals g of x at the point 1, 3. Another question asks, when is f of x less than or equal to g of x? So when is this f of x less than or equal to g of x? Well, we have a linear function. And again, we can write this out. We have this f of x minus 1 is our f of x function. We're looking at when is this less than or equal to g of x, which was this negative 2x plus 5. I would solve this the same way as I would solve this as it was an equation. The only thing I have to worry about is dividing or multiplying by a negative 1, and that would change the sign. If you looked up here though, when we solved this, we never multiplied or divided by a negative 1. So I can see, I don't know if you can see, but this would be x is, my sign would be the same direction. X is less than or equal to 1. You could see this if we graphed them really quick. Let's just graph it really quick. F of x equals 4x minus 1. I know what my y-intercept is. That's negative 1, and my slope is 1. Oops. So my y-intercept is negative 1, and my slope, sorry, is 4. So if I rise 4, I would go over 1. So I get this line that looks like this. If I graphed my g of x function, so g of x, this was negative 2x plus 5. And so I have a y-intercept at 5. And my slope is negative 2. So if I went down 2 over 1, and I graph this, I get this line. We were looking at when is our f of x? When is that purple graph smaller than the red graph? And it said, we saw that it was for x less than or equal to 1. So this is where they were intersecting. Notice the y values here. These y values are going to be smaller than these y values for all x is less than 1. Okay, so we probably got through most of 4.1, if not all, but we're out of time. So I'm going to stop here. If I need to, I'll pick up a little bit and do a little more on Wednesday or Thursday. We are skipping 4.2. I might talk about it a little bit, but that's modeling linear functions. And we're going to jump into 4.3, which is quadratic functions next.